Hello, good morning. This is the team deliverable project number 3 with team Orion, search and rescue robot swarm. My name is Joseph Ortega, and I'm responsible for the detection robot.
I'm Sean Coden. I built the lifting robot.
I'm Elias Strom, and I built the first aid robot.
And I'm Sarah Bashada, and I built the rescue robot.
Brief introduction, problem statement: design a search and rescue method for military personnel in an active combat zone that will minimize risk of human loss of life and injury. Some additional context surrounding the problem are that many robots on the market today are capable of performing many functions. However, a lot of them are missing key requirements, basically such that all the robots are not able to do all the tasks at one time. So what this project hopes to solve is by adding more robots which can perform individual functions. And the benefit here is that this will be able to aid more personnel, and the type of aid can be customized per scenario. Some customers directly will be the military personnel who will be operating and receiving the aid of the robots. Some indirect parties will be other people hoping to use this in their fields, and any applicable policymakers at parties like that. Introduction continued. Some of the design requirements will be that the designs need to be able to detect personnel within 20 feet. They need to be able to clear large obstacles and clear a pathway for the other robots to provide aid. They need to be able to render first aid, and they need to be able to safely evacuate the wounded personnel from the area. So must travel at least 5 miles without needing to recharge. Going along with the individual robots specifically, starting with mine will be the detecting robot, equipped with passive infrared sensor, can detect changes in the ambient infrared light exposure to detect humans while the robot is being remote controlled from central hub. The lifting robot will be able to clear large obstacles and be able to traverse rough terrain in order to create a path for the other robots. The first aid bot will be capable of administering different types of first aid and can communicate to the central hub to determine what other types of aid will be required. And the rescue bot will be highly durable and will be able to safeguard the wounded personnel, carrying them to safely, and will also be receiving inputs from the central hub. Going into the detecting bot, the mechanical design is about 3 feet long, about 3 feet tall, about 4 feet high. It does use the passive infrared sensor to detect personnel, and is battery powered, and it does have all-terrain wheels. And the original concept was going to utilize a servo motor to be able to rotate the camera about an axis. However, with the remote IR sensor being able to drive in all directions, forward, backward, left, right, the sensor was left out in order to promote the accessibility of the design with fewer moving parts. So here's the circuit design, including a 9-volt battery, the Arduino board, the passive infrared sensor is attached. The DC motors are there to control the wheels, and the remote controlled infrared sensor enables forward, backward, left, and right motion. Here's the flow chart, which is stating that the robot will be turned on from the central hub. If an input is received via remote control, it will follow the input commands to move in the direction specified. If it has detected a person via passive infrared sensor, then it will notify the central hub with the GPS coordinates. If it does not, then it will continue searching until a time when it is decided that they're done searching, and they will also return to the central hub for shutdown, or they will continue searching for another personnel who might need assistance. The code here is primarily to work with the infrared sensor on the remote control to control the forward, backward, left, right movement, as well as sending GPS coordinates to central hub in the event that the passive infrared sensor does detect personnel. And I'm so sorry. Going into the circuit demonstration, I'll now start the simulation. I will activate the DC motors, showing forward motion, backward motion, left motion, right motion and increase speed up, speed down, as well as the passive infrared sensor is activated as indicated by the red lights in the sensor. And we can see that when the target is within a field of view that is pre-programmed, that this PIR sensor activates and the signal can be sent to the central hub. That concludes my demonstration for the detection bot.
And now this is the lifting bot. The lifting bot measures 6 feet long, 6 feet wide, and 7 feet high, with an arm span of 5 feet from the body. It lifts debris, obstacles, and possibly injured persons when it receives a signal. It features all-terrain tires and a counterweight on the rear for balance. It receives power via solar panel. An Arduino directs signals through the circuit. A distance sensor detects objects in the path. A DC motor drives the all-terrain tires. A signal from the central hub is sent to engage the lifting mechanism, which is modeled here as a push-button actuator. Servo motor drives the lifting arms when the signal is received. The lifting robot will continue to move forward until it detects an object or person within 60 inches. It should be noted that if the object or person is detected within 24 inches, it will reverse course. When the person is in lifting range, or objects in lifting range, the robot will await a signal from the central hub. When the signal is received, it will engage the lifting mechanism. When another signal is received, it will disengage. Shown here is the circuit. We will begin the simulation. Here, the object is out of range, and the robot is propelled forward. Here, the object is too close, so we reverse course. Here, we are in range to lift the object. The signal is received, and the lifting mechanism is engaged. With the object out of range, the lifting mechanism can be disengaged. And that's the lifting robot.
I am Elias, and I created the first aid robot. For my mechanical design, it includes 4 propellers, LED lights, and a PIR sensor in the front, so that you could recognize that it's the front and so it could detect motion. And it also consists of 8 robot arms. This is the electrical circuit, which consists of an Arduino board, a breadboard, bridge motors, batteries, the IR remote and sensor, the PIR sensor, DC motors, LEDs, servos, and flex sensors, as well as the solar cell. So not only does it have battery power, but it will also draw from solar power. Here is the Arduino code, the first chunk of it. This is the second chunk, and a lot of it consists of the communication via the IR remote. When you press a certain number, it will continue with a certain command. And here we have the flow chart, and it will start, it will scan for the input from the remote. So depending on the button, it will perform that certain command. However, if there is motion scanned by the PR sensor, then it will stop the motion and certain lights will go on for certain sensors. Here is the 3D model. And then to start the simulation, start it, and it'll print out certain things to the serial monitor, and so we'll print GPS coordinates. If I press 0, I can go ahead and press print the GPS coordinates again. If you press 1, the arms will flex and it will be signaled with the green LED. 2 is to release. And you could also see the motion in the motor. If I would like to stop it manually, then I'll go ahead and stop. And each of these commands are printed. So for movement of the propellers so that the robot is able to fly, there's these motors right here. So if you move forward, you press 5, backwards, left, and right. Then you can manually stop it with 3, or if it's a text motion, it'll automatically stop the robot. And then the yellow LED will blink as a warning. And that is my robot.
I'm Sarah, and this is my rescue robot. So the rescue robot is 8 foot by 3 foot by 3 foot long. It consists of a 7 foot long hollow body, which will hold a person to transport to safety. And then there is also a 1 foot long front compartment that's going to house most of the electrical components. It has continuous tracks, and it has a tailgate on the rear of the robot body that will fold down to load a person into the hollow body. It is also made of aluminum armor to help keep the person it's transporting to safety as safe as possible. There is a force sensor embedded in the surface of the hollow body of the robot, and that's used to sense when a person's been loaded into the robot for transport. And then on the front of the robot, I've depicted everything that's going to be housed in that 1 foot long front compartment. So Arduino IR sensor, a distance sensor, GPS sensor, and battery. And then there are 2 DC motors underneath that are going to control the movement of the continuous tracks. So these are the circuit components. There is going to be an IR sensor, a remote, a distance sensor. This is the Arduino battery, H-bridge, 2 DC motors, and then a force sensor. And then in terms of activity, so most of its commands are going to be taken from Central Hub via the IR remote. The force sensor is going to continuously measure pressure applied to the robot truck bed. If the applied force value is greater than 450, then it's going to report its applied force value to the Central Hub. If not, it's just going to continue its current action. The IR sensor is going to continuously scan for input from the IR remote. If button 1 is pressed on the IR remote, then the robot moves forward. The distance sensor scans for obstacles directly in front of the robot. If the distance sensor detects an obstacle within 5 feet, then it will stop movement automatically and report a stop status to Central Hub. If not, then it continues its current action, which is in this case moving forward. If button 2 is pressed on the IR remote, then the robot turns left. If button 3 is pressed on the IR remote, then it turns right. If button 4 is pressed, then the robot stops movement. If button 5 is pressed, then it moves backward. And if button 6 is pressed, then the GPS sensor detects the robot's current location in terms of latitude and longitude, and then reports that robot's location back to the Central Hub. So this is just everything that I mentioned in the flow chart in Arduino code form. Okay, and then I'm going to go to the demonstration now. Okay, so simulation. All right, so I'm going to turn on the sensor here, and it's there is an obstacle, but it's greater than 60 inches away from the robot. So when we press the button 1 on the IR remote, we're going to see forward motion on the DC sensors here. Now, if the obstacle is less than 60 inches away, we see that the DC motors have stopped and reported a stop status on the serial monitor. Now, at this point, to move around the obstacle, they can, hit button 2, which will turn left. And then button 3 is turn right. There's also button 4, which can do stop status automatically. That stops all movement on the robot. Button 5 throws the robot into reverse. Okay, and then button 6 will report a GPS location back to the Central Hub. And then for the force sensor, if we apply maximum force here, we can see that the force value is being reported back to Central Hub. And that is my rescue robot.
Collectively, the process begins with the search bot. The search bot runs its process, and once an injured person is detected, The rest of the team is dispatched. The team approaches the target. Lifting bot process is engaged. Once the target has been reached, a decision is made as to whether aid can be given. If it can, the first aid robot renders its aid. If not, we go right to the rescue portion of the mission. Or once aid is completed, we go to the rescue portion, in which the lifting bot places the person in the bed of the rescue bot. The rescue bot then runs its process. And that's the collective behavior.
So this design adds value for different target customers. This kind of robot swarm will reduce the risk of wounded military personnel, and it also grants the ability to humans who are unable to access certain areas. It also reduces the number of military personnel required in a combat zone, and it reduces the fatigue of certain types of military personnel who would exhaust their efforts.
So in terms of what we would have done differently on this project, looking back in retrospect, we probably would have picked a simpler collective task for our robot swarm, which would have reduced complexity of the design. A few of us did have to include several different types of sensors and multiple actuators. So in retrospect, we probably would have picked some robots with a less complex design. We also would have modeled each robot to look more similar in terms of physical appearance, since they would be sold as like a swarm or a unit. We would have designed each robot to be more adaptable and resilient to unpredictable environments, and we would have developed more intercollaboration between the robots.
And so basically, in conclusion, for Team Orion's robot swarm concept, right now, currently in the marketplace, there are a lot of robots that attempt to do an all-in-one robot package. But what we're attempting to do here is to have 4 robots that have different capabilities per robot, which is going to enable the central hub to be able to have a more tactile response to any situation. For example, there might be situations where you know in advance where the area needs to be cleared, only send that robot. You know where the aid is required, only send that one. So the ability to customize the method in which the robots are deployed is one of the main advantages that this project was hoping to tackle. So hopefully by watching this, you, the viewer, have seen what we are going for here with this project and can see that we have demonstrated the ability to have a unique team, a unique swarm of robots that are going to either collectively collaborate and work together, or can be deployed individually in order to assist wounded military personnel on the battlefield in a safe and effective manner.